To learn, we need to engage. The word engagement has many different meanings in education, but here I mean to be caught and held in a learning opportunity, similar to paying attention to something or someone that we can learn from. From one moment to another, what we engage with has a lot to do with our emotions, including our motivations. To understand how this works in the brain, we need to think about communication between our cortex and those subcortical structures deeper in the brain. This communication operates in one direction through these subcortical emotional centres influencing the operation of our frontal lobes, which are so important for our conscious reasoning. The communication also works in the opposite direction, since our conscious reasoning and our cortex can influence the operation of these emotional centres and how their signals are processed. For these reasons, we represent this communication with a two-way or bidirectional arrow. There are many myths about emotion in our brain, such as each of us having three brains, the idea we have an aggressive reptilian brain, an emotional mammalian brain, and we need to suppress these two to let our primate brain flourish so we can be intelligent and human. This idea, however, does not reflect how we know the human brain operates, or what we know about evolution. In fact, something like a cortex and a set of subcortical structures has existed ever since our closest ancestor was a fish. And in the evolutionary line that leads to humans, the cortex has just become more connected with these subcortical structures so involved with our emotional response. Emotions are so bound up with reasoning that many scientists think we should no longer think of them separately. The close relationship between emotions and learning was illustrated recently in an experiment that we undertook at the University of Bristol. We scanned the brains of students as they were revising a curriculum consisting of many topics including science, zoology, maths, music, history. We looked at what happened as we made their learning more like a game, in which, in one condition, they competed with their friend in the control room, answering revision questions in return for points that were then gamed on a wheel of fortune. They learnt more in these gamified conditions, but we also saw increased activity deep down in the brain's reward system. This is a section imaged through the brain when the students were doing nothing more than learning for an exam, but showing left and right parts of the reward system increasing activation when students knew their learning was part of a game involving winning points, as compared to when they were just learning for an exam. However, while it was generally true that on the whole gamification increased reward system activity, increased engagement, increased learning, it wasn't true for all of the individuals that took part in our experiment. A minority did not increase activation in their reward system, did not improve their engagement, did not improve their learning. And there's an important message here. Big differences exist between individuals in terms of their brains, how they respond emotionally, and how they learn. This image looks at a similar slice of the brain when adults were receiving feedback about a writing task that they were undertaking. When the learners were being told how well they were doing and receiving positive rather than negative feedback, we see greater activation in the reward system, as we might expect. And the size of this increase varied across individuals and predicted how much was learnt from the feedback. So these studies really do emphasise how all of our brains are different in terms of how they engage with learning. A lot of different experiences can stimulate our reward system and cause us to want to approach a learning opportunity and direct our attention towards it. And a lot of those experiences involve rewards. But these rewards don't necessarily have to have great value in terms of money, for example. It turns out that the maximum response of the brain's reward system corresponds to the maximum available reward in that situation, essentially the best that is on offer in that context, whether it's 1 gold star or 10 gold stars. But also, continuously receiving the same reward for the same achievement can actually diminish the impact of that reward on our brain, because the response of the brain's reward system is very relative to expectations. So offering a rich range of social rewards in the classroom that are constantly refreshed with new ideas, such as different forms of praise and tokens acknowledging achievement, can be immensely important for engagement and for learning. Novelty also impacts on the reward system in much the same way as reward. The unusual, the unexplored, can drive curiosity and learning very effectively. And those elements of luck or chance in a learning game, so-called uncertain rewards, can have a greater impact on the brain's reward system than wholly predictable ones. Scientific research has also established that simply providing some element of choice can stimulate the reward system, even if we don't know exactly what we're choosing. So, for example, being asked to choose your own question, even if you can't see the options available. And sharing attention with another can also increase activation in the reward system. And this may help explain why working together with others can be so engaging and helpful for learning. In contrast to these positive emotions around learning, fearfulness can actually cause us to avert our attention away from the learning opportunity. We've evolved a primitive fear response that helps us avoid threat and keeps us safe. But in the classroom, fear, whether it's fear of the teacher, of the subject, or of our classmates, can actually cause us to disengage from learning. Once again, this is about our subcortical structures, and particularly a structure called the amygdala, impacting on our frontal cortex, but this time reducing our ability to learn and even to use and apply the learning that we have achieved. To understand how this happens more fully, we need to discuss working memory, our ability to temporarily hold information in our conscious attention. There is so much information that we could attend to in the outside world, on top of that already stored in our memory inside our brains. If we put all of that information in a container, it would have to be a very big one. Of course, we don't want to attend to all this information all the time. That would be quite confusing. So it would be useful if some sort of bottleneck only allowed a limited selection of all that information to enter our consciousness at any one time. That bottleneck is actually provided by the brain itself, by our working memory networks, chiefly involving our frontal lobes. These allow us to consciously maintain and operate on a limited amount of all the information available, a type of conscious but limited workspace, but one that is large enough to keep us reasoning and learning most of the time. But anxiety disrupts these working memory networks, and we can then consciously hold and operate on less information. The bottleneck effectively narrows, so we have more difficulty attending to new information and are less able to recall and consciously attend to what we've already learned and stored in our memory. Finally, in terms of engagement, it's good to know about brain plasticity, the ability of the brain to change in response to the environment. We know that when we learn, the connections or synapses between neurons change their strength. That's called synaptoplasticity. But actually, the changes that can occur in the brain due to learning are even more dramatic than this. Just over a few weeks of intensive study, the brain can change not only just its function, but also its structure the relative size and shape of its different parts. In one study, the brains of medical students were scanned before carrying out an intensive 3-month period of daily study for an exam. They were scanned again a couple of days after the exam, and then a third time 3 months following the exam. Immediately after the exam, it was shown that large regions of the parietal lobes had increased their grey matter. And in these sections through the brain, we see parts of the hippocampus, a region of the brain that has general importance for consolidating our learning, has also increased. Interestingly, the hippocampus did not show its full increase immediately after the exam. It reached a new maximum 3 months later, which the researchers blame on stress. The hippocampus is sensitive to stress, and it seems the anxiety around the examination may have delayed the full benefits of the learning on the growth of the hippocampus. But the most important message here is that the brain doesn't provide some fixed biological limit to what we can achieve. The things we decide to do have a big impact on how it develops and our capacity for learning. And promoting that important message has been shown to have a positive effect on educational achievement through encouraging children to believe in their own potential, to not give up, and to try their hardest. So clearly, plasticity is an important message for teachers and for learners. So we have now 4 key scientific concepts about engagement that can provide insight into classroom practice. In this video, we've learnt that every brain is unique, what causes an approach response in the brain that can engage us in a learning opportunity, how fearfulness and anxiety can cause us to disengage, and why plasticity is a concept that every teacher and every learner should know about.